In the last class, we have shown that in alternating current circuits, the voltage level can be easily stepped up or stepped down using a transformer. A transformer, we have shown, is a set of coils that are magnetically coupled. In order to couple a set of coils, we make the following arrangement. We choose a core made up of ferromagnetic material and put winding on them. So, if we connect a voltage source V1 here, there will be a current flowing into the coil I1 and this will generate a voltage V2 in the second coil by the principle of induction, that is Faraday's law. The coil in the first coil, the current in the first coil produces a flux that circulates through the core and links the second coil. Since in alternating circuits the flux is also alternating, there is a rate of change of flux linkage in the second coil, as a result of which a voltage V2 is generated. So, this is the basic operating principle of a transformer. We can get good insight into the operation of this transformer if we make certain simplifying assumption. For example, the first assumption we make that the windings are lossless. Windings are lossless, that is, they have zero resistance. Of course, that is an ideal winding. The second assumption is regarding the core. We assume that the permeability of the core is infinity. Tends to infinity, which means in order to establish any finite amount of flux, the current drawn will be 0. This implies the permeability of the core infinity implies the BH curve of the material is the y axis, that is, for any finite B the corresponding H is 0, therefore, the required ampere turns is 0 and hence the current is 0. As a corollary of this second assumption, since the permeability of the core is infinity, there will also be no leakage in this construction, that is, all the flux produced by coil 1 will be confined inside the core and there will be no flux that will be flowing through the air. Since all the flux will be flowing through the core, it will all the flux will also link coil 2. So, the third assumption, which is not really a new one, but a consequence of the second assumption, is that there is no leakage flux. So, a transformer for which these assumptions are made is called an ideal transformer. Now, this ideal transformer is a conceptual device. You can understand that no such practical transformer exists for which all these three assumptions hold. However, the introduction of an ideal transformer as a conceptual device does help in understanding how a practical transformer works, and we will later on relax this assumption and try to arrive at the model of a practical single phase transformer. But for the time being, let us spend some time to find out what are the consequences of these three assumptions and how we can analyze a single phase ideal transformer. As we have mentioned, when a voltage V1 is applied across coil 1 of an ideal transformer, a flux phi m is established in the core. However, in order to just establish this flux, no current is drawn from the source, that is, under this condition I1 is identically equal to 0. Then we should also conclude that the voltage induced across coil 1 E1 must exactly balance the applied voltage V1 so that the current is 0. Now, by Faraday's law, E1 is given by N1 d phi m dt, where N1 is the number of turns of coil 1. Let us assume that phi m in steady state is given by the expression phi max sin omega t. Then E1 is equal to N1 omega phi max cosine omega t. Similarly, the induced voltage E2 in coil 2 will be given by E2 equal to N2 d phi m dt. It is to be noted, since in ideal transformer there is no leakage, the total flux linking the coil 1 and coil 2 are same. Both are given by phi max sin omega t. If I write in phasor notation, that is, I want to find out the RMS value of E1. So, V1 equal to E1 equal to 2 pi by root 2 N1 F phi max. This is the well known formula 4.44 N1 F phi max, and V2 similarly E2 equal to 4.44 N2 F phi max. Therefore, what we can say about a ideal transformer? If we have an ideal transformer, where we apply a voltage V1 across its first coil with number of turns N1, then the induced voltage on the second coil with turns N2 is related to the voltage induced in the first coil by the following relationship. E1 equal to V1 and E1 by E2 equal to N1 by N2. Not only that, E1 and V1 are in phase, E2 is also in phase with E1. The phasor diagram can be drawn as follows. The previous calculation we have shown, if the flux waveform is given by the time function phi max sin omega t, then the induced voltage is given by the function n1 omega phi max cos omega t. Now, cos omega t leads sin omega t by an angle of 90 degree. Therefore, we can draw the phasor diagram as follows, taking the flux to be the reference phasor. The voltages V1, E1 and E2 leads it by 90 degree. So, this is the phasor diagram of an ideal transformer at no load. No load since no load has been connected on the secondary side. Now, suppose I connect a load on the secondary side of impedance ZL. Obviously, since there is a induced voltage here, current I2 will flow, which will be determined by the magnitude and phase angle of the impedance ZL. However, as soon as the current I2 starts flowing in the second coil, by Faraday's law, it will try to oppose the very cause which it is due, that is, it will try to send a flux which is opposite to the flux established by coil 1. As a result of which, the total flux linking coil 1 will become phi m minus phi m2. So, the total flux linking coil 1 will reduce, hence E1 will reduce. However, since there is no impedance between the applied voltage and the coil, there will be current drawn from the source V1 of such magnitude, so that the induced voltage across coil 1 always balances the applied voltage V1, otherwise this current will keep on increasing, which means the flux produced by coil 1 will now change to phi m1, and in steady state phi m1 minus phi m2 will still be equal to phi m, so that the induced voltage E1 and E2 does not change. So, what will be the magnitude of the current I1? Obviously, if phi m1 minus phi m2 is same as phi m, then phi m2 is produced due to an ampere turns of N2 I2. The ampere turns N2 I2 produces the flux phi m2. Therefore, this ampere turn must be cancelled by the ampere turns of the primary coil, so that the net flux still remains at phi m. So, this should be equal to, so the current drawn from the source must produce a cancelling ampere turns N1 I1, so that the flux produced in the core remains constant at phi m. Therefore, we can say the N1 I1 should be equal to N2 I2, or I1 equal to N2 by N1 I2. This is sometimes called the reflected load current I2 dash. Therefore, when we put a load on the secondary of an ideal transformer, a reflection current I2 dash flows in the primary side, so which completely cancels the ampere turns of the secondary side. The relationship is N1 I2 dash is equal to N1 I1 equal to N2 I2. Therefore, we have the following relation in the phasor. Again taking the net flux linkage phi m to be the reference phasor, we have seen that under load condition E1 and E2 remains unchanged, that is E1 still is equal to V1 and E2 is given by E1 by E2 equal to N1 by N2. The current I2 is determined by the load impedance ZL. The current I1 will be in phase with I2 and its magnitude will be I1 equal to N2 by N1 I1 I2. This is the phasor diagram of the ideal transformer under loaded condition. So, for a ideal transformer we have seen E1 by equal to V1, E1 by E2 equal to N1 by N2, E2 equal to V2 equal to ZL I2 and N1 I1 equal to N2 I2. In other words, from this relation we can show V1 I1 equal to V2 I2. That is, an ideal transformer is a pure energy converter whose input VA is always equal to the output VA and the voltage and current are transformed by the turns ratio, that is V1 by V2 equal to E1 by E2 equal to N1 by N2. Similarly, I1 by I2 equal to N2 by N1. This relation holds for a ideal transformer. As we have mentioned, an ideal transformer is a pure energy converter and it is a conceptual device. It cannot be made in practice. So, a single phase practical single phase transformer is an approximation of an ideal transformer. Where are the differences? We had made three assumptions while formulating the idea of an ideal transformer. That is, we said that the windings are lossless. No practical winding will be lossless. There will be some resistance in every winding. How do we? Similarly, the core of a practical transformer will not have infinite permeability. It will have very high permeability, but not infinite. Therefore, even under no load condition, a practical single phase transformer will draw some current to establish the flux in the core. This is called the magnetization current. And third, as a result of finite permeability of the core material, there will invariably be some leakage flux in the single phase practical transformer. The leakage flux will circulate through the air and it will link only the coil that produces that flux and not the other coil. We will shortly see how to incorporate this into the model of a practical single phase transformer and how to develop the model of a practical single phase transformer incorporating the ideal transformer. But before that, let us turn our attention to some of the constructional details of a practical single phase transformer. The figure on your screen shows the left hand side shows the outward appearance of a practical single phase transformer. This can like appearance is due to the casing. The actual transformer is inside the casing. The actual transformer is inside this casing. These protruding parts are basically insulators through which external connection is made to the transformer inside. Now, if this is cut open, inside we will find the actual transformer, which is this object. Let us have a closer look of how this looks like. If we take a closer look, the practical transformer consists of a iron core, this member, on which a set of windings are placed. So, the main parts are a core and a set of windings. Taking a closer look at the core, we will find that this core is not a solid block of iron, rather it is made of a large number of thin plates of steel sheets which are cut in a particular fashion. Here it is shown that these steel sheets are cut in E and I shapes. Then many such E and I steel sheets are placed together to form the core. Now, this is done, these are called transformer laminations. The transformers are laminated in order to reduce the eddy current loss. Now, you are all familiar with the mechanism of eddy current loss. If there is a coil which produces a alternating flux, the flux flows through the core, different parts of the core. Since this is an alternating flux, it produces circulating current around them. Iron being a conducting material, a finite amount of current flows through the core and it causes loss. By laminating, we tend to increase the resistance of the circulating current path, so that the loss is reduced. This is called laminating the transformer core. Almost all practical power frequency transformers are laminated. Now, this shows the different types of laminations that can be used. Now, here we should say that this is just one shape of the core. There are basically two types of core that are used with single phase transformer. One is called the coat type core, another is the shell type. The difference is here the windings are placed on the core, that is the cores, the windings surround the core. In the shell type construction, it is rather the core that surrounds the winding. So, these are the two different construction of the core, one is the core type, another is the shell type. In both cases, in order to have good coupling between the primary or the primary and the secondary or the HV and LV winding, they are both made into different sections and intermingled. Here you can see that both the windings are divided in two parts and placed on both the limbs of the core. In the shell type construction, each of the windings, the primary and the secondary, are divided into different sections and then they are alternately placed, so that the coupling between the total winding is good and the leakage is kept to a minimum. If we look at the cross section of the central leg, then this is what we will find. The inside hatched portion shows the transformer laminations. On the lamination, usually a cylinder will be placed, which is made up of insulating material, so that it provides insulation between the core and the winding that will be placed next. The low voltage winding is placed on that insulating cylinder, and then once the complete low voltage winding is placed, then there will be another cylinder which will enclose the low voltage winding, and on top of which the high voltage winding will be placed, by keeping a gap between the low voltage winding and the high voltage winding, which provides for a duct for the cooling medium. The transformers while operation carry current, and hence there will be I square or R loss in both the windings. That heat needs to be taken out of the transformer, so that the temperature rise of the transformer can be maintained. Therefore, paths must be provided for the cooling medium, usually oil, to flow through the core and the windings. This is the purpose of the duct in between. So, the core, as we can see, has a strange shape like a cross. This is called the cruciform core. The reason is simple. The LV and HV winding both are circular and they are placed on cylindrical surfaces. The purpose of making this a cruciform rather than a square or a rectangle is to be able to utilize the most of the area inside the cylinder. For very small transformers such as these, even rectangular or square shaped cores are used, but as the transformer rating goes higher and higher number of steps are used, so that the periphery of the transformer core approximates a circle and the area inside the winding cross section is fully utilized. Now, coming to the windings, there are many different types of windings that are used with transformers depending on their voltage and current rating. For single phase transformer, usually 3 types of windings are used. For the low voltage winding, for a given kVA, you can understand the low voltage winding voltage rating is less, but the current rating is large, for which normally 2 types of winding, either a cylindrical multilayer or a helical winding is used, while for the high voltage either a cylindrical or a crossover winding is used. This picture shows the diagram of different winding arrangement. The low voltage winding are usually made up of rectangular conductors. It may be a single conductor or a large number of strips taken together and wound on the insulating cylinder of the low voltage winding. Between turns, another set of duct and insulation will be provided, on which a second layer can be wound. For the high voltage winding will usually have a large number of turns, but its current rating will be small. They can be still made up of rectangular wires or even circular wires. In the crossover winding, generally high voltage windings are divided into several groups, and the groups are wound separately and then they are connected in series to form the high voltage winding. Each group can have many number of turns and they can be arranged in multiple layers. Therefore, to summarize the constructional details of a single phase transformer, we can say that the main parts of a single phase transformer are the core. This is usually made of silicon steel and can be either hot rolled or cold rolled. For large rated transformers, normally cold rolled grain oriented or CRGO steel is used. For smaller transformer, hot rolled steel is used. This is silicon steel. The purpose of the core is to provide the path for flux, high permeability path for the magnetic flux, and their cores are of two types. The transformer core can be of coat type or shell type. The next important part of a transformer are the windings. There are two windings in a transformer. Normally, in a two winding transformer, there will be two windings. One is the LV winding, another is the HV winding. The windings are made up of aluminum or copper conductors, either round or square cross section. Square cross section conductors can be made up of solid conductor or multiple strips connected in parallel. The LV winding are usually of two types. One is the cylindrical or helix. The HV winding can also be of two types, either cylindrical or crossover. The next important constructional feature is the insulator. Insulators are used in different places of a transformer and they are classified either as major insulation, which are between, let us say, core and the LV winding and the HV winding, and the minor insulation, which are usually between the turns of a same winding or the layers of the same winding. Now, there are different types of insulation material that are used. For example, press board cylinders, then paper, transformer oil. At different purpose different insulation are used. The insulation material are characterized by their maximum temperature at which they can maintain their insulation properties, and this is the weakest constructional component of a transformer, and more often than not the quality of the insulator will determine the reliability or even the size of a transformer. Other than these three main constructional elements, there are many other elements that are used. For example, the bushings. The bushings are these protruding elements through which external connection is made to the transformer. These are usually porcelain cylinders, hollow porcelain cylinders with disc shapes through which the connecting conductors are placed. They can be for high voltage, they can be oil filled or they can be of capacitor type. So, bushing is provided for external connection, and then cooling arrangement. For small transformer, separate cooling arrangements are not provided. The cooling is provided by the tank itself through in which the transformer is placed. For large transformer, they are usually immersed in transformer oil, so that heat can be extracted from inner parts of the transformer, that is the core and the LV winding which is inside the HV winding. For even larger transformer, external cooling pipes or fins may be provided. For even larger 3-phase transformer, forced cooling by oil and with fan cooling can be provided. So, a large number of cooling arrangements are possible, and for depending on the power rating of the transformer, a suitable cooling method is chosen. And then you will find protection arrangements. Which are found in the form of, for oil filled transformer, for conservators, and then explosion vents, Buchholz relay, and then lightning arresters, and different circuit breakers and relays. So, these are the essential constructional elements of a single phase transformer that we will normally find. Now, coming to the comparison with an ideal transformer, there are, as we said, that for conceptualizing an ideal transformer, we made 3 assumptions, that is, the windings are lossless, the permeability of the core material is infinity, and there is no leakage. Now, none of these 3 assumptions hold good for a practical single phase transformer. So, we need to relax these assumptions one by one and arrive at a model of a practical transformer. So, let us see. Let this be the ideal transformer. It is easy to account for the resistance of the practical transformer coils. They will appear as lumped resistance on both the in series with both the coils. Let us call it R1 and the resistance on the other side R2. These are the resistances of coil 1 with turns N1 and coil 2 with turns N2 respectively. However, it is more difficult to relax the condition of infinite permeability. We said due to infinite permeability in a ideal transformer, all the flux produced by the coil remains inside the core. So, in an ideal transformer, let this be the flux phi M1 produced by current I1 and this is the flux phi M2 produced by current I2 and we have seen that phi M1 minus phi M2 remains constant if the applied voltage on coil 1 is constant. However, in a practical single phase transformer, since the core is not infinitely permeable, there will always be some flux which will not flow entirely through the core, but part of it will flow through the air. This is called the leakage flux, call it phi L1. Similarly, there will be leakage flux produced by current flowing in the second coil phi L2, which will link only coil 2 and not coil 1. So, what is the total flux linking coil 1? Phi 1 equal to phi M1 plus phi L1 minus phi M2. Similarly, the total flux linking coil 2 phi 2 is equal to therefore, the voltage induced in coil 1 is N1 d phi 1 dt equal to N1 d dt of phi M1 minus phi M2 plus N1 d dt of phi L1. keeping the analogy with our discussion with the ideal transformer, let us call this term to be the induced voltage E1, then N1 d phi 1 dt equal to U1 plus N1 d phi L1 dt. Similar equation can be written for the other coil, N2 d phi 2 dt equal to N2 d dt of phi m1 minus phi m2 minus N2 d phi L2 dt. Now, phi L1 equal to N1 I1 divided by the reluctance of the leakage path RL1. Similarly, phi L2 equal to N2 I2 by the reluctance of the second leakage path RL2. This can be written as, therefore, N1 d phi L1 dt equal to N1 square by RL1 dI1 dt and N2 d phi L2 dt equal to N2 square by RL2 dI2 dt. The term N1 square by RL1 is called the leakage inductance of coil 1 L1 and N2 square RL2 is called the leakage inductance L2. Therefore, N1 d phi 1 dt equal to U1 plus L1 dI1 dt and N2 d phi 2 dt equal to E2 minus L2 dI2 dt. Calling the applied voltage V1 and the terminal voltage V2, then we can finally write V1 equal to R1 I1 plus L1 dI1 dt plus E1, whereas E2 equal to V2 plus R2 I2 plus L2 dI2 dt. This set of equations give the model of a single phase transformer.